So, well, we're going to start the second activity on the internet. Now we have it's an honor to have with us Dr. Eduard Grasa from Spain. He's working with the internet for many years. So thank you very much for accepting our invitation, Dr. Eduard.
Okay.
So, you can start the talk.
Yes, okay. Okay, so thanks a lot for the introduction and for inviting me to this nice event. So what we'll try to do during this speaking slot is to give you an overview of our vision on what are the major problems with the internet and a potential solution we are working on called RINA. And trying to keep the talk at high level, so anything you may have more questions on or want to know more, just I will give you my contact details after the talk, so you can feel free to email me, or the people we are working will be happy to answer your questions. Also, I guess there will be some time for questions after the talk. I will be able to answer online as well, but if you want after also. So, what we'll try to make during this roughly 1 hour is to talk about computer network architecture and why it's important. So RINA, the recursive internet architecture, this solution we are working on is a new computer network architecture. So the first thing to ask ourselves is, what is network architecture? Then we'll try to see what is the current one, what are the main flaws, and how we can get a better one. So this should be the program. So let's start for the first question. What's the network architecture? So it's an easy question, but it's not so easy. So what is architecture in general? Forget about networks now, let's talk about just architecture. So if we look at the dictionary, it's just a style of design and method of constructions for building buildings and other physical structure. So the architecture provides a set of patterns and methodology that guides building designers in carrying out their tasks. So when someone has to build, let's say, a cathedral or a shopping mall or anything, it doesn't have to start from scratch. It already knows that there are some patterns and rules that it has to follow in order to be successful in the building this. So for example, we have the Gothic architecture, which has some elements of the architecture is that it had tall designs. There was flying buttresses also as a structural element, pointed arcs, vaulted ceilings, airy interiors, and so on. So with that element of the architecture, which are invariant with respect to the building, so we can find these elements in all or in most of Gothic buildings, we can build many different buildings with different requirements. So we have city halls, palaces, cathedrals, fish markets, and so on. Another example, if we look at an architectonic style that is closer to my city, in this case, Barcelona, we have these elements like the Catalan vault, plus huge heavy use of iron, use of bricks, asymmetric, curvy lines that remember of nature. And with that, again, you can build many different buildings. So music halls, parks, houses, hotels, and cathedrals, like the famous Sagrada Familia. So if we recap, what is architecture? Architecture provides a set of patterns and methodology that guides building designers to do their task. And what the architecture captures, these rules and patterns, are what are invariant with respect to the specific requirements of each building. So they are rules that you can apply in designing any kind of building. Okay? So let's remember this definition. That is architecture. Is it right? So then to find what is a computer network architecture, first we should answer what is computer networking. So, and to do that there are two questions that are useful. So first one is, what service is, so who are the users of networking services? What are the endpoints of communication? And usually people may think of interfaces or physical machines and so on, but that's not really the user of that. Users are applications, okay? So all Networking is between applications, or if you want to be really precise about it, instances of OS processes or equivalents, right? Whatever the platform is, if it's a sensor, or if it's a high-end server, even if it's a router, anything that is using networking services is some form of an instance of an application. And what kind of service is networking providing? It enables distributed computation. So what it does is remote data replication. Okay, so you have an application that is in one place, another application that is in another place, and if the network was perfect, it would copy all data from application A to application B, providing zero packet loss, zero delay, and infinite capacity. Of course, networks are not that perfect, so they all introduce loss, delay, and have a limit on the capacity they can handle. So we can see networks are just large data copying machines that provide a communication service to instances of applications. Therefore, we can characterize networking as inter-process communication, right? It's a service that allows two processes to communicate wherever they are. And this is not a new view. This was the view that was held by everyone at the beginning of, or at the first steps of networking. That the sentence is from Robert Metcalfe, who was the inventor of Ethernet. But if we look at documents from design documents from that era, beginning of the 70s, we also see this IPC model of networking and in the ARPANET design team, in the INWG, which was the first international network standards group, with people from the ARPANET, from CCLADS, and from UK networks being built at the time. And also it is at the original TCP specification. So if we can have a first conclusion on network architecture, we can see that network architecture provides a set of patterns and methodology that guides network protocol designers in carrying out the task, so that they don't start from scratch. They know what are the rules that they have to fulfill in this universe of network protocol design to be successful. And another important thing is that network architecture captures everything that is invariant with respect to specific requirements of each individual network. So it doesn't matter if you're building a cellular network, a wireless network, a data center network, an ISP network. If you're dealing with network architecture, you're dealing with the rules that will be useful to build any of these. So general rules and patterns provide distributed IPC services to any application over any physical medium. If you are looking at particular applications of architecture for a particular buildings, then you are not doing architecture anymore. You are doing a specific buildings or specific networks. Okay, so this is our problem domain, and this is what we are trying to address here, because that's what, as we will see now in the next section of the presentation, many of the problems that have to be solved or that can be improved in the current internet have to be solved at the architecture level. So what is the current network architecture and what are the main flows? So let's just start looking at this structure. And a structure basically means structure in distributed systems basically means layering. So current network models are loosely based on the OSI reference model, right? We have all been, if you have done some networking course or you are doing that, you have all been told that this is the 7-layer model where you have applications, presentation, session, transport, network data link, and physical layers. And that was the OSI model. But in fact, this was not the final OSI model. This was the initial one, and it was wrong. And even in OSI documents, they corrected that. And they have a model, layered model, that is this one. So this is the OSI, the real or the final OSI network architecture. When you have applications, so they figured out that these 3 upper layers was just one, the application layer. Then you have transport, and the network layer was divided into 3 layers. As we will see later, this had a use, which is being able to have routing at the internet link and routing at the network layer separate. And then we have the data link layer divided into medium access control and logical link control, as well at the end, the physical layer. This is OSI, so but today in the internet, what is the architecture? Also, it's difficult to, so it's not something universal because there is no formal architecture, and this is part of the problem, right? If you look at different sources, they will talk about internet architecture, TCP protocol suite, and so on, but there is no formal architecture. But more or less, all of them come to this model. We have application layer, the transport layer, the internet layer. Sometimes people call it the network layer, depends, but it means the same. And then the data link layer, which is divided in these two on the physical, so this is the same as OSI. And here are the major standard bodies that deal with these layers. So from internet app, we have the IETF and others as well. We have W3C and so on. For the lower layers, the layer 2 and below, we have IEEE and others as well. And for cellular networks, which are a specific industry, there is a specific standard body called CGPP that deals with everything below the internet layer and gateways to the internet. So this is the structure we have. What are the problems of this structure? So we can say that the internet is not really an internet, but it's a large network with it's a large concatenation of networks, but not an internet. If we look at the model, this model we have seen here, and we apply it to an internet, so we have here one network of one provider, another network with another provider. What we have here is that this provider network can have different physical media, and that we have these layers here managing these different physical media. This may be Wi-Fi, this may be DSL, this may be Ethernet, and so on. So you have different technologies managing different physical media. But if this network wants to have their own routing that may or may not be based on IP, or their own addressing, which is separate from the internet, it cannot do it because there is no intermediate layers here. So it just went from the layer 2 to the internet layer, and there's no network layer in between. Then this causes problems, as we will see now. And on top of that, we have transport and application. Here we have the OSI model, but let me go to the next slide first. So what is the problem here? If the network wants to do its own non-IP forwarding, so independent from other networks and from the internet, or hide internal routers from the internet so that they are not visible and not exposed to the internet routing changes or security threats, then you have to do some ad hoc extensions, and you end up with things like MPLS that you have to insert between the internet and the lower layers to be able to do some forwarding that is just based on your network policies and is independent of IP. Or you have to add tunneling protocols, which there are all sorts of them, like GTP for mobile networks, IP in IP, MAC in MAC, and so on. So almost every standards development organization is designing its own solution for its problem domain independently. And the problem is, it's okay for a domain, but when you have to mix all these technologies together, it's a complexity. It's very complex. It becomes very complex, and you need to be. Note that this was already covered in the OSI architecture. Since OSI had these network layers here, so as we see, the OSI network layer was divided into these 3 layers. These 2 of them were used to be able to have forwarding that is just network independent from the internet, and also to be able to have here some error and flow control protocol that allowed, for example, if this network is, let's say, very low quality, like a radio network, for example, and this very high quality, these protocols here can bring the error rate to something that is more or less similar to this one. So that when you have to do end-to-end transport here, you don't have problems such as the ones TCP has when it has to mix, it has to handle flows that go over mobile, over radio links and over fixed links. So the OSI model was an internet model, but the internet model we have today, the internet architecture we have today, it's not really an internet. It's a concatenation of networks with the same routing scheme. Another problem we have with this structure is that we have a fixed number of layers, and sometimes more are needed between the transport applications. And when this happens, we need to introduce new concepts, again, like overlays, VPNs, virtual networks, and so on. So the simple model we had here is, again, becoming more complex. We have MPLS, we have VLANs, we have Q in Q, we have GRE tunnels, we have lists, and so on. So again, everybody is doing their own extensions to fit their problems, and when you mix this together, it's chaotic. And if we look at inside each layer, the problem becomes worse because there are many solutions, many protocols that are independently designed. So for transport, we have TCP, UDP, SDP, and so on. And these protocols, although they are similar, they do not leverage a common structure. So they are independently designed, which means they have to be independently implemented, and so on. And more often than not, you have unexpected interactions between these protocols because you design them independently, but then they have to work together, right? So when you deploy them, there are also, well, this is the usual problem with deploying new protocols. There are also sorts of unforeseen interactions. You have to fix them, and so on, which translates again into complexity and cost. And this is something that some people, at least some people in the IETF, especially the old guys, is aware of. Like this person here, Roscaron, was a veteran of the IETF, and when he was departing, he was showing his worriness about this complexity growing and growing and so on. And this is something that can be really problematic because complexity makes all other problems worse. Makes security worse, makes scalability worse, and so on. But even if these protocols are designed independently, do they have any structure? Like, can we classify the protocols in some categories? More or less, yes. So we have data transfer or data plane, these protocols that are associated to every single packet, like multiplexing, scheduling, forwarding, addressing, and so on. For example, IP is data plane protocol, Ethernet data plane protocol, and so on. Then we have data transfer control protocols or functions, which are loosely associated with the data transfer ones, but they are not per each packet. So functions such as flow control, congestion control, transmission control. And finally, we have the protocols or the functions that manage the data plane, which, depending on the SDO, were called layer management functions, IEEE, for example, or control plane functions in the IETF. So this is functions to manage the functioning of a layer, like, for example, authentication, access control, routing, resource allocation, security management, and so on. So we can see that there is some structure, and we can leverage that later when we look into designing an architecture that has more unifying power than one we have today. Again, this is just this graph. This chart shows the number of RFCs per year that are being published by the IETF. And as we see, one would expect that if networking was reaching some level of maturity or consolidation, you would have less and less RFCs per year because you are consolidating the technology. But this is not the current trend at all. So something else that shows that we have a protocol explosion and complexity problems. Another set of issues is related to naming and addressing. Today, in our internet architecture, we don't have real application name. The application name is just a synonym for an IP address. The internet layers or the network layers just route on IP addresses. So when you look, for example, at a URL like our company's website, educat.net, this URL is a domain name that has a domain name that gets resolved into an IP address by DNS, which is an external database. And network layers allocate flows between pairs of IP addresses, which are assigned to interfaces. And this complicates multi-homing, as we will see, and mobility, as we will see right now. So transport layers know nothing about application names. Interfaces are assigned IP addresses, but also are assigned MAC addresses. As we'll see, this is also a source of problems. So, first problem is multi-homing. So imagine here we have a server. So we have a server application here, a server that has two IP interfaces with these addresses, and a client that is where a client computer where this application, the blue one, is accessing the red one. So they allocated a TCP connection, and it is between this IP address and this IP address. And now let's imagine that this interface, 1.1.1, goes down. What happens? You still have reachability to the server because you have another interface here. But the problem is that the network doesn't know that 1.1.1 and 1.2.1.1 go to the same place. To the network, they look just like two interfaces, and it doesn't know that they are assigned to they are part of the same physical computer. So the network cannot reroute. To fix the problem here, you would have to issue a DNS update, then allocate another TCP flow, and so on, which takes, even with dynamic DNS, it can take in the order of a few minutes. So here we can see that the network doesn't support multi-homing. There are all sorts of protocols to be able to fix this issue. But again, the issue is very simple. Instead of assigning addresses to interfaces, you have to assign addresses to the node. The node being the protocol machine that will remove the header of the protocol. So in this case, the header of the IP protocol. In this case, if you send packets to 1.1.1.1, or 1.1.1 is this node, it doesn't matter that this goes down, because the network is not routing interface, it's routing to this node. And it doesn't matter which point of entry to the node uses. So with this very simple change, you have multi-homing for free. The problem with multi-homing doesn't stop there, because it also makes mobility difficult. First problem with mobility is to move, you need applications that have an identifier that is stable across networks, right? If I am moving from one place to another and I lose my name, it will be very hard to find me if my name depends on where I am, right? So the other problem is that to make routing scale, network addresses needs to change as the host attaches to different networks, because otherwise you need to keep all sorts of home addresses and tunnels and so on to be able to keep the connectivity. But the problem is that in the internet layer there is only one identifier, the IP address, and it has to change. And so the IP address is both used as for routing and also to identify applications, as we have seen before. So allow addressing to allow routing to scale, but it has to stay stable to allow applications to move without breaking flows. Clearly, you have a big problem here. And again, there are all sorts of solutions to make this work. Over IP, which uses tunnels, proxy over IP, same thing. GTP, more tunnels, which is basically creating a huge layer 2 subnet so that even if the application moves, it doesn't move in the IP layer. You have Lisp and so on. And again, this is very simple to fix. If you have, if you have more than one identifier, you have application names that are independent of addresses, and your root of network addresses, this problem becomes trivial again. So we see that with a good structure, you can improve the situation of mobility and multi-homing. Last but not least of the problems, there's the application API. As we all, anyone that has programmed or used any network application has used the sockets API or some framework that below uses the sockets API. So this is the universal de facto application API for accessing network services. Sorry. And we see that this application is not, let's say, this API is not very well designed, because with API it will expose a service and hide the implementation, so that you can change the implementation without the clients using it being aware of it. But in sockets, sockets expose what is a transport protocol that is available and forces applications to choose it, right? You have to choose if you use a datagram or if you use a TCP connection. This is a big problem, because when you want to add new protocols, applications have to be aware that these protocols are there and have to explicitly choose them, which is a big barrier for deploying new transport protocols that are better than TCP, for example, in many situations like SCTP and so on. Another problem is that addresses are exposed to application, which is a security problem, because then it's easier for them to forge them or to hack them as well. And the third problem is that there is no way to request for the application to request what QoS it needs to be able to work. So applications can just use a reliable flow using TCP or use a reliable flow using UDP, but they have no way of specifying what is the maximum loss they can tolerate or the maximum delay they can tolerate and so on. So they have to, since the network will not provide this information, they have to adapt, complicating application development as well. And this is something even the ITI is working on it. There's a group called TAPS, Transport Services, which is trying to improve the API so that it's really agnostic about what kind of transport solution you have below, and it just focuses on the abstract characteristics of the service. So summing up, we have a network architecture that has problems in its structure, in the protocol design. We have seen that there is no commonality in developing protocols. Naming and addressing is flawed. Application API exposes the internals. And there's more problems. We don't touch security because of all of the other points. Security is problematic, or network management. Again, the more complex is a network, the more complex it will be to manage it. But for an introduction to the problems is enough, and it is okay to complain, but you have to provide solutions as well, alternatives. So let's look how we could construct a better network architecture. So summing up, what do we want? We said architecture provides invariants and rules. So what we want is as much invariance as possible in the architecture. So network designers have to do less as possible, right? The more commonality you have, the more tools you have in this architecture toolset to design specific protocols for specific networks, the more common the networks will be, and the less errors the network designer can make. So what we have today is the opposite. We have an architecture that has few patterns, few invariants, few building blocks. Some of them are broken. And this forces us to design a lot of protocols because we use networks in many different environments. And the problem is that we end up with too many protocols, too little commonality, and that brings all these problems. So what we want is a bit the opposite. Architecture with as much patterns and invariants as possible, as much building blocks as possible, and less protocols which match more commonality, so that you can have a set of elements that are universal and that you can mix and match to design specific protocols. With this, then you would have much simpler networks because they will be much more better together, and since they will be more equal, they could be easier to understand as well. So this is what we want. Then can we achieve it? Let's look at it. Let's start with the application API. We said at the beginning that we could characterize networking as just something that provides distributed IPC services to instances of applications. So what kind of application API we will need for that? So what we would need is applications need to request for these instances of communications, which we can call flows, for example. So we have a need to allocate and deallocate flows, and to write data to these flows and to read data from these flows, right? This is pretty straightforward. Then what we need also are application names that are location independent. What we said before, right? You need names that don't depend on where you are attached to the network, so that the network can locate the applications and allocate the flow to the right instance of the application. So we need this allocation API will allow application A to allocate a flow to application B, and the network will figure out where B is, which is the address that I have to use or to route the packets from A to. Also, applications need to be able to specify the requirements for their flows. What is the maximum delay I can work? What is the packet loss ranges I can use, and so on, so that the network can choose the right protocols and adapt to provide an optimal service. If they can, otherwise they can fall back to whatever is there. But at least networks will know what is that the application wants, and will not have to do dirty hacks like doing DPI or guessing port numbers or stuff like that to be able to infer what the application wants. So we have been picturing the network here like this box, but what is the network, right? It's what is it? It provides IPC services, but what is its nature? So it executes in computers running operating systems. So it executes on PCs, laptops, routers, sensors, smartphones, tablets, switches, and so on. Has instances. Protocols have instances distributed through many machines, exchanging information and collaborating. Right? You have routers, you have PCs, you have servers, everything with instances of networking talking together via distributed protocols, just like the web, Skype, email, and so on. So the network is nothing special. It's just a distributed application itself, which is specialized to provide IPC. So we don't have to differentiate between applications and the network, other than saying, okay, other than that, just to say the network is just a distributed application that provides IPC. But other than that, it's just a distributed application. It has instances, it uses below other instances of communication, and so on. So we'll call this application a DIF, a distributed IPC facility. But if we have a single DIF for our applications, like here, if we just have a single DIF for our applications in the world, it's not very scalable. We need to isolate different scopes. We need to manage, as we saw before, communications in a single link, communications in a network, communications in an internet, communications in a VPN, and so on. And we do this via layering. These new concepts here, what we have is multiple diffs, just providing IPC services to each other. After all, a diff is just a distributed application, right? So we have a diff here that is providing IPC over this link, another diff here that is providing IPC over this link, and on top of them, another diff that is providing IPC over these two routers, and on top of them, another one. So this could be a network, this diff could be a VPN, this is a link, and so on. But the key thing here is that we have a building block, this diff, that provides the same API, regardless of where it is in the layer stack, and it repeats as many times as you need. So we went from a model in which you had a fixed number of layers, each layer different, with a different API, with different functions, to a single layer, called the diff, that repeats as many times as you need. So you don't need to introduce new layers. If you need 5 layers in your network, you use 5. If you need 7, you use 7. If you need 3, you use 3. This is up to the network designer, not to the protocol specifications. And it is universal in the sense that it provides the same service regardless where it is. So we can have a structure with a single type of layer that provides an IPC service that repeats as many times as needed by network designer. What the layer does is, what this diff does is allocating resources and manage the IPC services over a given scope. It can be a link, like here, it can be a network, it can be an internet, it can be a VPN, and so on. So what the layer does is to allocate resources, memory buffers, scheduling capacity, bandwidth, to the flows that this layer provides, which are competing for these resources. So what the layer does is have policies to be able to allocate this capacity to different flows based on different requirements, for example, different QoS and so on. So we have a better structure now and a better service model and application API. More simple, but yet more powerful as well. So still some work to do. We have protocol design, naming, analysis, and so on. So let's move. What protocols do we have inside different diffs? So if a diff is a distributed application, how we can organize its functions? Okay, remember that what we are looking is to have as much commonality as possible that is independent and have everything that is independent of particular networks grouped together. And remember that we said before that protocols can be organized in protocols that do data transfer control, or layer management, or the control plane. So what we want is to limit the variability of protocols to the bare minimum. And to do that, we apply a technique that is called separation of mechanism and policy. And what we do is take the protocols and see what mechanisms do they have. So mechanisms are the parts of the protocol that are fixed. For example, an acknowledgement is a mechanism. And the policy is the part of the protocol that can change. When to send an acknowledgement is policy. If I take this mechanism and I configure it differently, I can have acknowledgements like in TCP, like send them after every packet, or send them after a timeout, or like in UDP, don't send acknowledgements never because this is unreliable, or combinations thereof. So we can, if we do this for all the mechanisms in the protocols, we see that we cannot have the same protocols in each diff, but we can have one protocol framework for data transfer and one protocol framework for layer management. And we'll see this in this next slide. So within the diff, we just have two types of protocols. One, EFCP, the error and flow control protocol, which provides, you can think it sort of a configurable IP plus TCP UDP. So IP, configurable transport plus network layer together, which from which multiple data transfer protocols can be generated. So you have a generic header here, which doesn't have specific field values, like it has addresses, it has QRID, it was connection point on this, and so on. But in each layer, you can decide what is the size of the fields of the address, if they're unique addresses or not, what is the size of the fields of QSID, and so on. And also, you can plug in the right policies. If you plug in, let's say, window-based flow control, then you have something like TCP. If you plug, if you don't use flow control, you have something like UDP. If you plug in the transmission control policy, again, you have a reliable protocol and so on. But the point is that you have this basic protocol framework, and plugging just these policies, you can recreate, you can obtain the final protocols for your environment. But you have a common base that does most of the design and most of the specification of this protocol framework is in the base, not on the policies. The second thing is to have this unified control plane, or unified linear management. Today, each function in the control plane, like flow allocation, routing, security coordination, and so on, uses its own dedicated protocol. So you have OSPF and RIP for routing, for example, you have RSVPT for resource allocation, you have ICMP for control, and many others. What we have here is basically what all these protocols do is exchanging structured information and invoking operation on them. And then there's a function in each node that does a specific function of flow allocation or enrollment and so on. So for example, a routing protocol is 90% replicating data through a distributed database, 10% doing routing. So we have, and it's the same for any other protocol. So what we have done here is have a universal protocol that it just keeps a partially distributed database of objects synchronized, and then different callbacks are invoked for different functions. So we have a resource information base, which is the schema that defines this the set of objects that model the state of the diff, of the IPC process, which is the instances of application process that are part of the diff. We have CDAP, which is this universal control plane protocol, which just provides operations to be able to enable two applications to exchange objects and to operate on them. And then we have the read daemon. What it does is when it gets a CDAP message, it looks what object is being invoked and delegates the processing of the message to the object. So with that, we can create control plane protocols much easier, because 90% or 80% of what is currently in the specification is common and is just done once. If you want to do routing protocol, you just need to define what is the objects that are you going to exchange, what operations are you going to perform on them, and what happens when these operations are invoked. But you don't need to do your own serializing, your own protocol to exchange information, and so on. All of this is already done. So finally, let's just look at naming and addressing. And if this, so there's having a lot of work in this 3 years, but one of the best works from the beginning is looking at what are the objects that have to be named in a network for naming and addressing. And we have applications, right, that tell you what is going to communicate. So for example, I may have a web server, so the New York Times website here and a client here. Then these application names have to be location independent so that the client or the server can move and applications are still having the same identity and you can find them wherever they are. Then applications names are attached to the network at some point. Applications are attached to the network and attached to a node address. This node address indicates where the application is in the network. And this has to be location dependent. So it has to be an address, right? It has to tell you where the node is with respect to other nodes in the network so that routing can scale. Otherwise, you cannot aggregate. And also, but it has to be route independent, as we said before. It doesn't matter if this node can be reached through different point of attachment. It doesn't matter through which point of attachment I reach the node. The node still has the same address. And this way, you can handle easily multi-homing and mobility. And then there is the point of attachment, which is you just select at the hop before you as the way to reach this node address. Then routing is a two-step process. You have a sequence of node addresses. So to route from this application to this one, you have to go to 1, 2, 3, 4. And then at each node, you select which point of attachment you will use to reach the next one. With this decoupling, you can easily support multi-homing and mobility. And this is the problem with the internet. You don't have application names, all you have is an IP address. We don't have node addresses because the IP address is not assigned to the node but to an interface. And MAC addresses are unnecessary because IP addresses are assigned to interface as well. So there's a duplication here, and we are missing components here. And all this is fixed in RINA. This is an example that I'm not going to explain because missing time here. But it's in the slides, you can go through it. If you have questions, just tell me. But the point here, it just illustrates how to use the forwarding when addresses are assigned to interfaces like in RP or when addresses are assigned to nodes. So in addition to supporting multi-homing, the forwarding and routing tables are much smaller as well. And you don't need special protocols. Let's look into security. Another problem of today is that each protocol comes with its own security suite. So you have IPsec for IP, TLS for the transport layer, or for TCP basically, BGPsec for BGP, DNSsec for DNS, and so on. As a consequence, security is expensive, but brittle as well, because these protocols don't work in isolation, they work in combination. And again, since these solutions are independently designed, when you put them together, there are also all sorts of weaknesses that can be defeated and are defeated today. Instead, in RINA, what is secured is not the individual protocols, but the layers. So the distributed applications, you need, when a member of a diff wants to join, you do authentication and access control. When an application wants to write some data to the diff, if it doesn't trust it, it will encrypt the PDUs. And this is the same relationship that you have among all layers, because all layers are equal. They have the same structure. So you have a clear security model across all the layers of the stack, which is much easier to reason about. And you don't have to implement security per protocol, just per layer, which is much cheaper. Also, each layer limits the scope of connectivity. So each layer just allows you to reach a limited number of IPC processes. In contrast, in the internet, you assume that everything wants to be connected to everyone by default, always. And then you have to use extra resources to be able to isolate provide further isolation, like firewalls, ACLs, VLANs, VPNs, and so on. So again, it's a wrong assumption and expensive as well, because you need different kinds of means to be able to restrict the scope, whereas in RINA is already built in. And also the naming and addressing and there are aspects of the architecture that make it more secure, but we'll not go through it right now. We have papers published on that, so if you're interested on that aspect, I can provide more information as well. And finally, network management. You can imagine what's different of managing a network where you have an arbitrary number of different layers with an arbitrary number of different protocols that have been independently designed, which is hard to manage because it has little commonality, to managing structures such as the one as RINA, in which you have clear building blocks which are repeating all along, protocols that have been designed with commonality in mind, and so on. So management becomes much, much more simple because networks are much, much more simple. So, summing up, RINA is not a protocol, it's a network architecture resulting from a theory of computer networking, seeing networking as IPC and only IPC. We have a single type of layer with programmable functions that repeats as many times as needed by the network designer. It's called leaf. All layers provide the same services, which are instances of communications between two or more application instances. And you can, didn't talk about it, you can deploy it over, under, or next to the current networking technologies. So it's something new, but it can be, and it, of course, it needs to be compatible with what is already there, otherwise it cannot be deployed. There are some examples here that I will not cover because due to lack of time, again, they are in the slides that I will distribute. If you have questions, I will be very happy to answer them. So, question about deployment. You want to replace TCP/IP, how do you pretend to deploy this stuff? And the point is, this is not about replacing TCP/IP, but providing something new where TCP/IP doesn't do enough. And you can have it in many deployment use cases. In fact, we are seeing how long it takes to deploy IPv6 because it's the opposite example. IPv6 with very small improvements to IPv4, just a larger address space, but requires a clean site deployment because it's not compatible to IPv4. So the cost of adoption is really high. The benefits of adoptions are really low. In RINA, we use a different strategy. It can be incrementally deployed where it has the right incentives. So what it means that TCP/IP is not enough. And it can interoperate with current technologies. So you can use RINA below IP, for example, just like a better MPLS or a replacement of Make and Mac and so on. You can use it over an IP as an overlay solution, for example, such as VHLAN and BGRE, GTP, exactly. Or other technologies like that, or you can gateway to IP as well, or to TCP, exposing a RINA network as an AS if you wish to do so. So there are many ways you can deploy this and be compatible. There's not a problem. So if it is so fantastic, why it is not already out there? And of course, you have a full change. So getting something new adopted that takes such a feature that is so it takes such a fundamental change in the understanding, not in the deployment. Again, in deployment can be incremental, but changes in understanding takes time. Also, even more because people is just, in terms of investment, investors are looking most of the time at short-time revenue. So something that can take a much larger benefit but takes more time to materialize can be complicated to fund, but we're working on that. So what we are doing right now is implementing prototypes that we are using in our research projects, but they are open source, so you can also use them if you want. Here I'm going to mention one, which is called IRATI. It is built basically at the beginning for experimentation, but also so that it can be in the future a basis for a RINA-based product. So there are some characteristics. It is Linux implementation, which has the functionality of RINA split between the user space and the kernel. This is implemented in C and C++. And it can, here's the architecture. You don't need to understand this, just that we have some kernel modules. We can interact over UDP, so we can overlay RINA on top of UDP, of Ethernet VLANs of Wi-Fi. We are working now in a project to have RINA below IP in the kernel, so we can have sort of NPLS-like features. And what I'm going to do now is just show a quick demo. We have a tool called the demonstrator that basically allows you to instantiate and configure RINA in a single physical machine. So it allocates, it creates a number of virtual machines with RINA, with IRAT, with this prototype inside, and configures them in the topology that you specify. Here, for example, in this demo, we have 107 VMs with a data center topology, in which we have a data center fabric div with this topology, and on top we have 8 VPN divs, each VPN with this one, with this topology here. And just to make it more visible and to show something more on slides. So what we have here is the demonstrator tool in the physical machine installed, and you can access the individual machines here. So what I'm going to do is this server here and this server here, and just start an application that does echo. So this is an echo server, and this is an echo client. Here I'm accessing this server 1.1 and starting the echo time server. So it's a ping-like application. And this is another server, and in just starting the echo client. Which will do 1,000 pings with this packet size, and we see that it's doing the pings, and so on. So if we look here, here is another node, another virtual machine in this configuration that I have accessed, and I'm just going to show the console to be able to see. So what we have here is this different, each line here is an IPC process, or an instance of a different div, and these are all shims, so IPC, so special adapters that allow us to put RINA on top of Ethernet. So this is on top of all these different interfaces. And then we have this IPC process belonging to the data center fabric div, and these two IPC processes belonging to these two different VPNs that are going through this node. So we see that all the different layers have the same concepts, the same technology, the same protocol frameworks, so it's much easier to configure and use networks and understand networks this way. Last but not least, I will be providing, so there are some pointers here about research projects, this open source implementation, which is available on GitHub, and other ones. We have also simulators and other implementations, as well as some pointers for other standardization activities. If you are interested in playing with it, we have a number of tutorials in the GitHub site, which is here. So we have a number of tutorials. And using the demonstrator tool is really easy to set up because you don't need to compile anything. You just need to download the demonstrator repository and use the configuration files as it is explained, and you can already access them and look at different nodes and so on. So to try the code, you don't need to compile anything. It's easy to do. And that's all. Thanks for explaining, and if you want, I have a few time for questions still. Oops, I cannot hear the are you speaking? As I cannot hear the audio. Still not hearing it. Still no lag. Let me join again just in case.
Pronto. Pode me ouvir? Puxa vida. Eduardo?
Oh. Yes, now I can hear you.
So thank you so much for your very nice survey on how is that because you have a very good perspective on very much. And I do believe a lot of things that because we have here one as well, we know our Genesis architecture, and it's very good to see that we have so many things in common.
Sorry, Antonio, the audio is a bit bad, and it's hard for me to understand what you're saying because I hear a lot of noise. Well, noise. It's with the microphone. It's complicated.
Are you
There's a lot of echo with a mic, you know.
Ele não está escutando muito bem, né? Talvez melhor mais perto. Can you hear now better?
Oh yes, much better, much better.
Because the microphone is not good, but I'm going to talk nearby the computer.
Thank you for that.
Thank you so much for your very nice perspective on current internet issues and RINA details, because it was great to us to see that what we are doing here has some very, very interesting similarities. We have here Nova Genesis architecture. We did a previous activity here about Nova Genesis last week. So it was great to see the common issues and different issues, and as well the perspectives you put, because when we change the point of view, it's much easier to see the point. So this was great, I think.
Yeah, that's really also. We are able to have people for 1 hour and open with open minds to be able to change the point of view.
Great. So I think we have time for some questions. If you allow us, are you open for the questions here? So just a second. Well, I have some questions, of course. I'm going to use the time. First of all, in the last activity we did here about future internet, we discussed so many issues. One of them is what we need to do to convince the community that it's possible to change the architecture or to have alternative for TCP/IP. What, in your point of view, can we do for this? Like what activities or initiatives we can do to demonstrate for the people that we can provide alternatives?
That's a very interesting question and a hard one. And our perspective have been changing through the years. So we have been involved in a number of let's say, standardization efforts in order to, disseminate this out to people, convince them. There's one in ETSI that we have been working in 1.5 years called Next Generation Protocols, where you would think people would come there with an open mind to change the protocols because part of it. But still, half of the group is still afraid or very entrenched with IP and just improving IP. So I think that what needs to be done is to deploy it, so build it and deploy it somewhere commercially. We have real users that you can go and see, because at the end, most of the questions or most of the challenges don't come from, oh no, this is theoretically wrong, this doesn't make sense, but okay, where is it running? Show me that this in practice can work, and so on. So the big showstopper, I think, is that first of all, you have lots of competition for attention. Lots of people working in different things that may look similar, and there are lots of papers and so on. So I think that the real what can get the ball rolling is to have some people adopting this in particular scenarios, for example, data centers or inside of small service providers, in some places where the protocol can be deployed in isolation, meaning it's not exposed outside, but it still brings benefits to the people using it. And then can people see where it's working there for real? And then with that, you have a much better basis for convincing, talking to people, going to the different forums, and so on. But for us, at least, what has been the major showstopper, and what we are trying to work on as well, is to have some, put it into the market, have some real users, and see for real how it works.
Fantastic. We discussed some things similar, but we don't have, for example, large demonstration or companies interested. But we are working to have this in future. I think it's great if companies can see the advantages in real, like to go to some demonstration and see the advantage of using new architecture.
Yeah, it's using proof of concepts, and proof of concepts, if possible, that are already showing interoperability and that deployment is not a risk. Putting it below IP and showing that it's really forwarding IP traffic, or on top of IP and showing that IP is forwarding your traffic, because this is many of the things that people is afraid. Okay, will it work really when I pull it with all the other stuff? So if you show that you have removed this risk already, then they open more their ears to listen to you, because you have to go through a set of mental filters that it is too big of a change, it needs to be compatible, and so on. So if you show that this is not a problem, then you get more attention and you can progress to the next phase.
Great. Another thing we discussed here was the need to cope internet policies from technologies. I got a scholarship for ICANN meeting, I think, Buenos Aires, 2015. I don't right, but the point is that today a lot of policies on internet are coupled with the technologies we use on internet. For example, for DNS, for WIS, and other issues. So in my report on this participation in ICANN, I took as a conclusion that we need to couple the policies from the technologies, so we can have new alternatives or the same policies. For example, what are the policies for domain names? RINA can be different technologies for the same policies. Do you think about this? Is it a possible way to also to convince people about new architectures alternatives?
Yeah, for sure should be a very good rule to decouple energy from to decouple policy from specific technologies, because the whole point of the internet being there is because it allowed it supersedes former already existing technologies. So if you want to keep it improving, you cannot allow the internet to become the next telephone network, right? So I completely agree with you. Legislation has to be aware of these issues and be as technology independent as possible. But I don't think that for any new protocols, the message should be we are going to try to change the internet, because then you first of all, you cannot really do that at once. So you can start deploying, as I said, deploy new stuff below the internet, over the internet, next to the internet. Even the concept of the internet, it's okay, it's a public address space using IPv4, IPv6, but if you look more at it, there are many parallel internets even today. So I don't think that the goal is to replace the internet. It's just deploy something new that works better, and whoever needs it will start using it. And if the old internet is okay for you, just keep using it. I mean, technologies have all a cycle, and there are still, technologies from X25 networks. There's still a number of them there, right? So there will be internet for years, but this doesn't need to preclude the deployment of something new. This is really the problem, and I agree with you. If policy precludes the deployment of something new, it's a problem.
Yeah, our idea was, the consensus here was that we should allow alternatives, but don't fight against or try to replace everything. The idea is to, okay, if you want to try this alternative, okay, go ahead. But we just ask for space to provide some alternative. And
exactly.
Of course, aligned with the internet policy. No one would like to change what we have on the internet. But what we want to do is to give some alternatives to use the other technologies for the same policies.
Exactly. Completely agree with you.
This is great. We discussed a lot of this in last activity here last Saturday, and it's great to see that we have a conscience on these points as well. Okay, great. I have another question that is, what about Internet of Things arena? Do you have something on this? What do you think about the Internet of Things?
Yeah, it's an interesting. So there's some colleagues of us. Sorry?
The question is, do you have someone working on Internet of Things for you?
Yeah. So some colleagues of us in Belgium have a Flemish, the Belgian government funded project to work on an implementation for constrained devices. And they are going to open source that as well, probably in the next 6 months or 1 year. But yeah, it's an interesting domain for RINA because since it's so adaptable, you can make very optimal protocols for the Internet of Things. Like many times, you may not need addresses in the protocol because you're just talking to the same gateway all the time, or you may not need flow control, or you may not need a lot of things that are by default there in IP or in other sort of protocols. You can have optimized protocols for IoT, but still keeping this common framework. In IoT right now, you have a lot of proprietary protocols, like ZigBee and stuff like that. So the idea here is that you can still keep this commonality with this generic protocol framework, but you can adapt it to the requirements of IoT. So you can remove anything that is not needed and come up with a very, very, very simple protocol that can be run in these days really constrained devices, and is still common to the core framework, let's say.
Great, great. So we are doing some work here on embedding Nova Genesis on IoT devices. So it will be great to see how people is doing this with RINA.
It would be good to learn about your work as well. So yeah, let's keep in touch after this event for sure.
Great, thank you. I will ask here if someone has another question. No, so I'd like to thank you so much for your time and opportunity to discuss with us. I don't know if you have some final message for the people here that is working on future internet.
No, I just first of all thank you for providing me this opportunity to speak about RINA to all these people that probably have never heard about it. So thanks a lot, and just keep your mind open and try to understand things. So don't assume too many things. Try to understand them in the field of networking, because you get surprises. Lots of things that you have been taught, just they are the way they are. They may not be. So just keep your mind open, and that's all. Thanks a lot.
Okay, so can you share the slides you presented now?
Yes, I will send you an email. Is okay?
Okay, you can send me by mail. I send it to the people here.
Okay, and if anyone has questions, my email will be there. So just feel free to ask.
Okay. I will put this for people here as well. So thank you so much. I hope to see you again at a conference, and probably there is time we don't meet. again, but probably we are going to meet in some conference in future.
Hopefully. And thanks a lot, and let's keep in touch. Bye-bye, good morning.
So great time. See you. Thank you so much. Bye-bye. Pessoal, acho que a gente pode encerrar a transmissão, né? Aí a gente poderia discutir um pouco aqui entre nós.